Hi everyone, my name is Gracielle Ann Villamer together with my group mates Jenny Ibarrientos and Francisca Louise Biares. Today, we will make a short video about the approximating areas under curves, illustrating net area from graphs, introduction to Riemann sums and regular partition, illustrating Riemann sum using graph, and illustrating Riemann sum using tables.
Hi, I'm Jenny, and I will discuss about approximating areas under curves and the net area graphs. Approximating areas under curves involves finding an estimate of the area enclosed by a curve and the x-axis within a given interval. Here's the one of the basic example that we will compute. Given interval using four left endpoint rectangles, we will compute the y is equal to x squared plus 3. We have the interval negative 5 to 1. The first we need to do is to find the width. How to find the width? Is it x divided by 4, which is the interval using? And the answer is negative 1.5. Here's the table for the x and the y. How to find the y? Um, it is because from there, y is equal to x squared plus 3. Kaya ito po ang mga, pag ginawa po yun, ito po ang mga magiging sagot. The next one is, we will multiply the y and width, and here's the answer when multiply it. And to add this all, the answer is negative 72. The net area from graphs is the total area between the curve and the x-axis, accounting for both positive and negative areas. This is the example graph for net area. The shade of green below the x-axis is called quote negative region, while the shade of yellow-green above the x-axis is called quote positive region. The value included in the positive region is 2 and 5, while the negative region is 9. Integral from a to b of f of x is equal to 2 plus 5 is equal to 7 minus 9 is equal to negative 2. So the net area of this graph is negative 2.
About Riemann sum left endpoint and right endpoint. Riemann sum left endpoint and right endpoint is a method of approximating the area under a curve by dividing the region into multiple subintervals and approximating the area of subintervals. Therefore, several ways to select sample points within each subintervals and two common methods are to use the left and right endpoints of each subintervals. For the example of left endpoint and right endpoint, let's use the same function fx equals x squared over the interval 0.2 and divide it into two equal subintervals to demonstrate both the left and right endpoint methods. First, plot the function fx equals x squared on a coordinate plane over the interval 0.2, divide the interval 0.1 and 1.2. For the left endpoint method, area of subinterval 1 f1x times delta x equals 1 times 1 equals 0. And for right endpoint method, area of subinterval 2 f2x times delta x equals 1 times equals 1. So the left endpoint method, total area is 0 plus 1 equals 1. And for the right endpoint, total area is also 0 plus 1 equals 1. So both methods yields the same approximate area under the curve fx equals x squared over interval 0.2 with two subintervals, which is 1 square units. Riemann sum partition. Riemann sum partition is a method of approximating the area under a curve by dividing the interval on which the curve is defined into the smaller subinterval or partition. Multiplying the sum of these function values by the each subintervals gives an approximation of the total area under the curve. As the number of division increases and the each subinterval approaches 0. Example of Riemann sum partition. Fx equals x over the interval 0.2 and divide it into 4 equal subintervals to demonstrate the Riemann sum partition method. Divide the interval 0.2 into 4 equal subintervals 0.0.5, 0.5.1, 1.1.5, and 1.5.2. For simplicity, let's choose the leaf endpoint of each subinterval as the same point. Multiply the function values by the each subinterval. Area of subinterval 3 fx cubed times delta x equals 1 times 0.5 equals 0.5. and the total area is 0 plus 0.25 plus 0.5 plus 0.75 equals 1.5. So using the Riemann sum partition method with 4 equal subinterval, the approximate area under the curve fx equals x over the interval 0.2 is 1.1 square unit.
So, illustrating Riemann sum using tables. It involves tabulating the value of the function at the specific point with each subintervals and using this value to calculate the area of corresponding rectangles.
So here are the example of Riemann sum using tables. F of x equals to x squared with the interval of 0 and 3 using the 6 sub-interval. So getting the function of x is equals to x squared, we will just square this value to get the answer in the function of x. 0 raised to 2 is 0, 0.5 raised to 2, 0.25, 1 raised to 2 is 1, 1.5 raised to 2 equals 2.25, 2 raised to 2 equals to 4, 2.5 raised to 2 equals to 6.25. Of x is 0.5. Why? Because 3 over 6 equals to 1 half. 1 half convert into decimal is equals to 0.5. Next, how will we get the area of rectangle? The formula in this is the length times width, which is the length is the function of x and the width is the area of x, or the delta of x. So 0 times 0.5 equals to 0. 0.25 times 0.5 equals to 0.125. 1 times 0.5 equals to 0.5. 2 times 25 times 0.5 equals to 1.125. 4 times 0.5 equals to 2. 6.25 times 0.5 equals to 3.125. How we get the Riemann sum for f of x equals x squared with the interval of 0 and 3 using 6 sub-interval. We will just add all of this. Area of rectangle 0 plus 0.125 plus 0.5 plus 1.125 plus 2 plus 3.125 is equals to. So that is the Riemann sum of f of x equals to x squared over with the interval of 0 and 3 with 6 sub interval is 6.875.